Have you ever walked along a beach and noticed tiny bubbles rising from the sand or water, almost as if the earth is breathing? It's a curious thing to see, but what if I told you these tiny bubbles could tell us something enormous, something truly explosive, about the forces that shape our planet? Today, we're diving into the intriguing connection between bubbling beaches and supervolcanoes. It's a story of hidden energy beneath the Earth's surface, and how those little bubbles could offer a peek into catastrophic forces. So, let's walk along the shoreline together, and discover how something as simple as a bubbling beach could unravel mysteries. Scientists are just beginning to understand what these signs mean. First, we'll explore the mysteries beneath the surface, what those bubbles actually are. Then we'll connect those signs to the giant systems deep below, supervolcanoes. Finally, we'll ask, can these tiny clues help us predict something huge? This video is aimed at students and educators, clear, visual, and evidence-driven. We'll use real-world examples, monitoring techniques, and accessible science. No dramatic scare, just the facts and the science behind them. Keep an eye on the small details. Nature often hides big stories in plain sight. We'll move from small bubbles to the history and behavior of supervolcanoes. Let's begin with the mysteries beneath the surface. Picture yourself at a beach, waves crashing, the salty air, and the sound of seagulls. But beneath the surface, something is stirring. Tiny bubbles rising from the sand or shallow pools. These bubbles are typically made of gas, often carbon dioxide. At first glance, it seems harmless, even peaceful, but these bubbling phenomena are clues to larger geological activity beneath your feet. They point to geothermal activity, heat rising from Earth's interior. Next, what is a supervolcano and why should we care? Geothermal activity occurs when heat from the Earth's interior rises to the surface. In certain places, that heat creates gases, CO2 or sulfur, that bubble up through water or cracks. Often these gases come from magma chambers deep below. At the surface, bubbling looks calm, but it can reveal pressurized systems underground. Gases travel through fractures, finding weak points in the crust to escape. These are the first signs of a pressurized magma system. So what is a supervolcano? A supervolcano is not a taller cone. It's a massive system with huge magma chambers. Its eruptions can reshape continents and affect global climate. Super eruptions can eject trillions of tons of ash and aerosols into the atmosphere. That can block sunlight and alter climate for years. They can trigger crop failures and wide-scale disruptions. Supervolcanoes don't erupt often, they simmer for tens of thousands of years. Magma and gas slowly accumulate, pressurizing huge chambers. Scientists monitor subtle signs over long time frames. That brings us back to the small bubbles at the shoreline. Gas chemistry and flux can tell us how active a system really is. They're part of the system's communication to the surface. So bubbles, fumaroles, and hot springs are not just curiosities. They're measurable symptoms of deeper processes. Let's look at two real cases scientists monitor closely. First, the Yellowstone caldera, one of the most famous supervolcanoes. Bubbling hot springs and fumaroles are common here. These are windows into the caldera's activity. Yellowstone's last major eruption occurred about 640,000 years ago, yet geysers and gas emissions show the system remains active. Scientists continuously measure gas composition and flux. Second, Campi Flegrei near Naples, Italy, another supervolcanic field. Here, bubbling mud pools and steam vents are monitored closely. Scientists track ground uplift, gas, and seismicity. Campi Flegrei has erupted many times. The last major event was tens of thousands of years ago. Recent uplift and gas changes prompt careful monitoring. Researchers use multiple data sets to assess risk. Both sites show how surface signs connect to deep magmatic processes. Next, we'll dive into the science of the gases themselves. Understanding gas chemistry is key to making sense of bubbling beaches. Let's look at how scientists read those signals. We'll discuss what rising or falling gas levels can mean, and how those tiny bubbles can be an early warning. The signals are subtle, global, and scientifically valuable. Now, the science. What are we learning from these gases? All spoken lines are subtitled for clarity. By studying the gases released, CO2, SO2, and others, scientists can infer subterranean changes. Different gases tell different parts of the story. CO2 often signals deep degassing, so too can show fresh magma ascent. Combined, they reveal pressure, temperature, and movement below. When CO2 emissions rise, it can mean magma or volatile rich fluids are moving upward. That increases pressure in shallow reservoirs and can change eruption probability. But context matters. Season, rainfall, and other factors can alter readings. Fumaroles and geysers are controlled outlets for gas and steam from subsurface systems. Their temperature, chemistry, and flow rates are carefully tracked. Changes can indicate deeper changes in the magma system. Scientists don't rely on gas alone. They fuse seismic deformation and gas data. Ground uplift often accompanies increased gas release. Satellites add a broad perspective to local measurements. Interpreting signals requires careful correlation across datasets. A single spike in gas may not mean imminent eruption without supporting evidence. Patterns over time are more telling than single observations. Let's revisit Yellowstone and Campi Flegrei with this context in mind. At Yellowstone, gas ratios and ground movement are closely tracked. At Campi Flegrei, uplift episodes have alerted scientists to changes. Yellowstone's monitoring network watches for changes in CO2 and SO2 emissions. Geyser behavior and gas chemistry give clues about shallow hydrothermal systems. Long-term trends help assess whether a chamber is pressurizing. Campi Flegrei poses a different challenge: dense population near a geothermal field. Small changes in gas or ground level can have major societal implications. Authorities use monitoring data for planning and alerts. Different systems behave differently. Context is essential. Some gas increases come from shallow hydrothermal changes, not from magma. Disentangling shallow from deep sources is a major scientific task. Measure, correlate, model. That's the basic scientific workflow here. Each dataset refines predictions and reduces uncertainty. Patterns over time matter more than single events. Models take these observations and test eruption likelihood scenarios. As gas and deformation increase together, probabilities rise. Forecasts are probabilistic, not deterministic. That uncertainty shapes how communities prepare and respond. Monitoring can inform planning and risk mitigation. Early detection of anomalous gas patterns could save lives. Could bubbling beaches really help predict super eruptions? They can be an important piece of a larger monitoring puzzle, but they are valuable indicators when combined with other data. To recap, bubbles point to gas, gas points to pressure, pressure may signal risk. Students and educators can use these examples to learn about Earth systems. Next, the science of prediction and the role of climate. We'll discuss how monitoring progresses toward practical forecasting and how human activity and climate might interact with these systems. Let's continue. Now, the latest science and what it means for the future. Scientists refine detection by calibrating instruments and validating data. Careful calibration avoids false alarms from environmental noise. Reliable data underpins any forecast. New models integrate physics, chemistry, and observations to improve forecasts. They test multiple scenarios to quantify uncertainty. Forecasts express risk probabilistically, not as certainties. Could bubbling beaches save lives? Potentially, if we detect meaningful trends early. Continuous monitoring allows detection of slow changes before crises. Think of it as an environmental smoke detector, one part of a safety system. But there are limitations. Weather, tides, and biology can affect surface gases. Data must be corrected for confounding factors to avoid false signals. Context is critical when interpreting any single observation. Climate change and human activity may influence volcanic systems in complex ways. Shifts in surface loading, like melting ice or changing sea levels, can alter subsurface pressure. Scientists are actively researching these links. For educators, simple monitoring experiments can teach data literacy in Earth systems. Hands-on data collection builds critical thinking about environmental signals. Include context, seasonal factors, instrumentation, and cross-checking. Supervolcanoes remain frustratingly unpredictable despite advances. They operate on timescales far longer than human lifetimes with complex triggers. That means we must remain cautious and evidence-based. Still, each validated measurement and model reduces uncertainty a bit more. New sensors, data sharing, and computing power improve our capabilities. Progress is incremental but meaningful for preparedness. In the future, monitoring could inform land use decisions and emergency plans. It could guide where to build and how to evacuate safely. Data-driven choices reduce risk. To summarize, bubbles indicate gas, gas indicates pressure, and integrated data informs risk. Measure, correlate, model, repeat. These are the building blocks of volcanic science. Students, use field observations to practice scientific methods. Explore public datasets from Yellowstone and other observatories. Start with primary data and peer-reviewed resources. Ethics matter. Communicating uncertainty responsibly is as important as the data. Avoid sensationalism. Present probabilistic forecasts with clarity. This protects communities and preserves trust. While unpredictability persists, science is improving our foresight bit by bit. Global collaboration accelerates progress in data sharing. Together we learn faster. So remember, Tiny bubbles at the beach can reveal enormous processes beneath. They're small pieces of a global scientific puzzle, and every measurement helps build understanding. If you investigate, follow safety protocols, and use established methods, handle gases and thermal sites with care and proper equipment, never approach hazardous vents alone. Teachers, integrate local observations with online data sets for meaningful lessons, use official observatory data and vetted scientific sources, and encourage curiosity and rigor. The Earth speaks in many voices. Listen carefully, measure precisely, and think critically. Thanks for watching. Sources and lesson guides are in the description below. Subscribe for more science breakdowns. Explore the data sets, and stay curious. As we come to the end of our journey along these bubbling beaches, I want you to think about something. When you're walking along a beach or hiking near a hot spring, those little bubbles rising from the water aren't just a curiosity, they're clues. Clues about the massive forces at work beneath your feet, forces that have the potential to shape our world in ways we can't even imagine. While the prospect of a supervolcano eruption may seem distant or even impossible, the bubbling beaches remind us that the Earth is alive and constantly changing. And by paying attention to these small, seemingly insignificant signals, we might just be able to understand the next big event before it happens. So, the next time you see bubbles rising from a beach, or hear the hiss of steam escaping from the Earth, remember, you're witnessing a message from deep within the planet, a message that could hold the key to our future.